And then I finally, in the beginning of this year, I finally had some time to actually do the data analysis. And so I'm going to present to you the data analysis and the kinds of questions that I was particularly interested in looking at. And so basically, we have this whole idea, especially with objects, that of viewing software as Lego, right? That the way that we write software is that we write small pieces, and then we compose the small pieces together to build larger systems. That's the metaphor of Lego. And we know, that to construct modular systems, there's small systems and there are large systems in Lego too, right? If you're a Lego builder, you know that there's sort of a skill difference that goes from building a little car to building the Taj Mahal. So I wanted to kind of explore basically this idea of programming in the small and programming in the large. And this is an old idea that has been around, almost as old as the Lego metaphor, whether there are differences of programming in the small versus programming in the large. And intuitively, we kind of know that there are some differences. In fact, way back then, 1975, there was a couple of authors that suggested that the way to build big systems, at some point you start to need what they call the module interconnection languages, right? Something external to the modules themselves to kind of specify how things fit together. And this was sort of an inspiration for a bunch of work in research, like architecture description languages and you name it, even aspect-oriented programming, you name it. So there's some idea that as systems get bigger, there's something going on in there that you kind of need to start thinking at a different scale. So I wanted to really explore that and understand that. Is this true? Does the scale of the software system affect the internal structure of the modules, or are modules basically scale invariant? Does anything about the structure of the internal modules change when you have a very large system versus having a very small system? So that's what I wanted to kind of explore. And in particular, there's 5 different things that I could unpack out of that bigger question. So one in terms of module size, are the modules of larger systems larger than the modules of smaller systems, or is there no difference? Another with respect to module type, so is there statistically significant variation in the mix of classes and interfaces? Do the bigger projects use more interfaces, less interfaces? Another one is internal complexity, and there are many metrics of internal complexity, cyclomatic complexity. I didn't have the cyclomatic complexity metric, so I went at it in other kinds of metrics. Another one is composition via inheritance. Does the scale of the project affect the use of inheritance, both in terms of how many classes are defined user inheritance and how many classes serve as the superclass of some other classes? And finally, the dependencies. Do larger projects use disproportionately more or fewer types from external libraries than the smaller projects? And with respect, for example, to JDK, for example, what happens with the use of the JDK as the projects get larger? So why does this matter? I mean, it matters because, first of all, it was bugging me for a long time. So it mattered to me because many times I was doing I've been doing large-scale empirical analysis of software for a while, and some of the metrics were really weird. And in particular, they seem to depend on size in a very strange way that I didn't quite understand. It basically suggested it was violating the principle that modules are scale invariant. And I wanted to find that out, whether what was really true or not. So it matters on all metrics on large and diverse corpora, but so there's confusing effect of size in software analytics, and this has been reported. I'm not the first one reporting this, okay? Size is at least confusing, if not confounding, factor in software studies. Another thing that I think it matters is to find principles of software as complex systems, and this would be evidence-based mathematical models of software systems. And again, this is not new. This is a type of work that started in the early 2000s by people not necessarily here, although there has been some work here in this community too, but these are people that tend to publish things like physics reviews letters that like to study complex systems, and at some point they found software to be an interesting area to study complex systems. And the other thing was the possible disconnect between the expectation and reality. So understanding why this disconnect exists. If it exists, it may lead to better languages or tools or at least more realistic expectations. So that's why I kind of went and sort of analyzed the data. So let me talk about the data set and the methodology. The data set consists of about 30,000 Java projects collected from Google Code as of the summer of 2011. It's about 220 million source lines of code. This is a subset of the Sorcerer 2011 data set. For maybe some of you don't know, let me publicize it. I provide large data sets. If you want to make empirical studies of very large code bases, you can come to my website, Sorcerer ICSS-PCIBU, and there's a variety of data sets that you can download. And some of them are pre-processed already, parsed in some other representation that is more amenable for certain kinds of analysis. So the Sorcerer 2011 is larger than just Google Code, but I focus on Google Code because it seemed that it had an interesting mixture of everything that people do with Java. So on the left, you can see a graph that shows the size of the project in log scale, so source lines of code. If you order the projects by their size, okay? If you order them by their size, this is a very nice sigmoid that you get. It's an interesting thing that I've observed in many other data sets too. Again, this is all evidence-based mathematical principles of software. You end up with sigmoids like this if you have a sufficiently large and diverse software data set. This here shows the histogram of project size. Again, this is all that you're going to see is in log scale. And I'll explain why. So this is basically, it says that average projects in here are about 10 to the third, so about 1,000 source lines of code. Between 1,000 and 10,000, that's where the majority of these projects lie over here. And all the processing of all these data sets has been done with the Sorcerer tool set that is available on GitHub. And that is also, the whole thing is packaged, not the data set is gigantic, but the tools and the small sample of the data set is packaged as the artifact that people can download also from my website over there if you want to play with it. All right, so let me explain a little bit about the statistical analysis and the methods that I use. So basically, I was looking for correlations, and I was looking actually for linear regressions, right? I was looking for, how the number of methods relate to the lines of code, okay? So I was looking for bivariate analysis. So linear regression models, and in particular, because of the nature of software that is highly skewed, right? Everything in software, if you have a sufficiently large data set, you find skewness, logs, sort of a lot of things that are very small and a few things that are very large. Okay? So because of that, the best space to do these kinds of analysis is not in linear space, which is on the left, but it's in log space, which is on the right. Okay, so basically what that means is that instead of fitting the linear model in just x and y, what you do is you find the linear model in log x versus log y, okay? And you find those parameters, and then if you want to kind of map back to linear space, which is where my head at least works better, you just do the math and revert the things, okay? So basically what that means, if you would find a line, the line that you find in log space is just like a line that you define in any space, which is the y equals some alpha plus some beta times the x, okay? Just so happens that in log space, the y is log of the variable and the x is log of the variable, okay? But then you do the linear regression and you find that line. And there's actually more variations that you can do. You can actually go a little bit more creative and do the linear regression, not in log, but in log versus log square, or in log versus log over. This is a sort of a guesstimation. You're trying to find the best fit and you just get creative. It's not very efficient. There are probably a lot more machine learning methods to find best fits for these kinds of things, but I didn't want to go there. So the question that arises is, okay, so once you find the line, how do you know that it's a good fit, right? So there are statistical tools that tell you. One of them is the, it's not here, one of them is the R square. Okay, so everybody sort of heard about R square. Whenever you do a fit of a line on a bunch of data points, R square sort of measures the error between the data points and the line, right? And so if you have a very good fit, you have a very good high square. And if you have a very low R square, that it means that the line doesn't explain very much of the data. Yeah, but R squared doesn't explain everything in these linear regression models. You actually need to look at the residuals and see there's kind of 4 kinds of residuals. I'm not going to go into details here. It's all in the paper. But there's 4 kinds of plots that help you visually inspect whether it's a good fit or not. And basically what you want is, on that, you want basically straight lines, okay, on those 3. And this one over here, you want kind of a gentle, sort of like this. Okay, along the diagonal line. Okay. So keep that in mind. This is how I kind of validated that how good the fit was. Okay, it's the R squares, the correlations, and the inspection of the residuals. Okay, so what did I find? So I'll just show you some of the plots. There's a gazillion of plots in the paper. Okay, as appendix, I just dumped the entire thing there. So this is some of the more interesting ones. So module size. So I found the linear regression of SLOC versus modules. And by modules, I mean classes and interfaces, okay? So if you count, over here is the number of classes and interfaces in each of the 30,000 projects, okay? Each of those dots. And on the y-axis is the source lines of code of that project, okay? So you do a linear regression and you get basically a line where alpha is 3.55, and the beta, which is the exponential, okay, is 1.09. Now, if this is linear in linear space, that alpha would be 1, okay? When we have that, the beta would be 1. When we have an exponent of 1, we basically have a linear relation in linear space. When we have a beta that is different than 1, if it's more than 1, then it means that the growth is superlinear. So as the x grows, the y grows faster. If you have less than 1, it's sublinear. It means that as the x grows, the y also grows, but slower. Okay? So basically what he's saying here is that the lines of code grow slightly faster than the number of modules. Okay, so it means that there's something funky going on in here, that as the projects get larger, they also get disproportionately more lines of code. Not just more lines of code proportionally, but disproportionately more lines of code. Okay? So let's go to another one. Methods, this is still also related to module size. Methods versus classes. This one, the beta is even higher, okay, 1.1. This means that as the number of classes grows, the number of methods grows even higher. So the bigger projects have more methods per class, basically. Here's another chart for module types, and this is just an example. So classes, interfaces versus classes. This is an example of an analysis that I did my best, but the fit is not very good. Okay, as you can see, R squared is only 0.52. Even the Pearson correlation is not super stellar. And you can see visually by the plot that there's something funky going on. This fit is definitely not very good, okay? And in fact, if you look, I tried many kinds of spaces to do the linear regression. I tried log, and then I tried log square, which is this picture that you see here. So it establishes a relation between the log and log square, not log long. And once you start getting these kinds of spaces, it's really funky what's going on, because actually if you map this back to linear space, the growth is not monotonic. So it's like you start high and then you go low and then you go high again. It's not a sort of a monotonic relation when you pass this back into linear space. If you so basically there's something funky going on in here that has some behavior that depends on the size, but it's not a linear dependency. It's something more funky. So if you just plug in some numbers, like I did, because I really wanted to understand. So if you split, for example, the very small project, going from the bottom, okay, very small project, which means it's like less than 20 classes, and you look at like the small ones, between 20 and 100 classes, and the medium ones, 100 and 1,000, large between 1,000 and 5,000, and the very large, it's more than 5,000 classes. And then those are the number of projects in my data set that fit within those parameters. So I want to point you out to the linear percentage, so the numbers in parentheses you can read, which are the more understandable ones, okay? So those are the ratio of interfaces over classes, okay? So basically what it says is that for very small projects, there's about 18% is the ratio. Basically, there's 18% is the interfaces over classes, okay? And then it starts going, and then it starts decreasing, okay? It goes all the way like to 6%, and then it starts gently increasing again, all right? So that's sort of how it goes over here. Like the very small projects seem to have very high ratio of interfaces over classes, and then it sort of goes down, and then the very large ones start to kind of want to grow a little bit. But again, keep in mind, the fit is not very good. So that means that the confidence of this result is not very high. So internal complexity, I think I may skip this one. So, but I didn't have cyclomatic complexity, unfortunately, in my data set. So I kind of went to it of trying to look into method calls versus methods, okay? So as the number of methods call increases, oh my God, okay. So let me read the paper. Okay. Inheritance, I'll show you this one. So inheritance is another one that was sort of kind of a whoop, okay? So I'll point you some of the numbers. So for projects with 2 classes, the prediction of that model was that it has 0.9 interfaces. For 10 classes, it's 3.5. So basically, it starts high, then it goes low a little bit, but then it starts it goes even higher. So basically, it means that the very large projects have about 68% of the ratio of classes defined using inheritance. Okay, so the larger projects use a lot of inheritance. All right, so I also have a bunch of slides on dependencies, but I don't have time to go to them. So let me just go. It's important that I make this very clear. So the project size affects some software properties in nonlinear ways, and I mean internal software properties of the models. Okay, so it's if we didn't know already, okay, it's yet one other piece of caution. Be careful with what kinds of projects you use in your empirical analysis of whatever it is that you are doing, because size really matters. It may matter. So given enough data points, like in my Google Code data set, this can be quantified and, if necessary, compensated for. So if you know your data set and you kind of know the relations, then you can kind of compensate. Okay? But the most important thing that I want to say is that the measured reality is not the desired reality. So here's what I mean by that. What I have is a collection of projects from Google Code. Okay? What I have done is to do linear regression models on that data set. This doesn't mean that what I found is the law. Okay? You know, I found that indeed there seems to be a little bit more complexity growing with the size of the projects, but doesn't mean that it has to be this way. In fact, we should continue to teach people to be careful about, you know, complexity going out of control, right? To modularize things well, and there seems to be some evidence that in the wild, people are getting a little bit lax on remembering those lessons, right? Another thing that I want to point out is that after I've done this data set analysis, we're actually analyzing another data set that has particular properties, okay? It's another very carefully chosen data set that we know that comes from a very nice organization that we trust the developers very much, are very highly skilled. And we're performing the same data analysis, okay? And we're finding differences. That's the interesting part. We're finding some differences. And there's clear signal that the complexity in that data set is actually a little bit more under control than the complexity in the wild. Okay. All right. So, and more important, the empirical data studies like what I did don't provide justifications. I don't know why. Okay. Why do those large projects seem to get out of control kind of complexity? I don't know. Okay. I can guess. I can make some conjectures, but I don't know. That would require another kind of study to kind of trying to find out. All right. So this is it. I include some papers I loved while I was doing this. And if you need to contact me, I can be contacted by many ways. Thank you.